Hello class and happy snow day. Of course, we don't get a lot of these in South Georgia, so I had to dress up for the occasion. Today with campus being shut down, we are going to do a pre-recorded lecture. So I'm going to switch between the document camera like this, where you can follow along with my work at home, and between the lecture notes. So you can see here is a shared screen of Adobe. So we're going to start with section 2.2, more on functions and their graphs. I do prefer to do this on the document camera. However, with the visual representation of the graphs, I think it is useful to see the same thing that I'm seeing. So I hope that you at home are following along with the printed out lecture notes and kind of filling in the blanks. So I'm going to do a combination of those two. So without further ado, we'll get right into it, and it's all downhill from here. All right, so just starting at the very top of 2.2, we are working on more on functions and their graphs. So graphs have a number of points of interest. So what we're going to talk about today is intervals of increasing and intervals of decreasing, intervals where the graph is constant. And we're also going to talk about local relative maxima or minima. So just to start off, if you're looking at this graph together, so you can notice here, kind of moving from left to right on the graph. So when I say left to right, I'm talking about starting kind of on the number line. So coming from like negative infinity to the right. Let's just observe the behavior of this graph. So this one in particular, it is a cubic function, so x cubed minus 3x. We call the shape of this a slide. And notice here, it starts by getting bigger and bigger and bigger and bigger up to about this point. And then it starts decreasing and decreasing and decreasing and decreasing to about here. And then finally it starts increasing again and again and again and again. Okay? And so we're going to talk about representing those as intervals. So everything like from the leftmost side of the graph, so all the way out towards negative infinity, it's increasing, increasing, increasing. It's getting bigger and bigger and bigger up until we reach this point, which is at x equals -1, so it's kind of stacked there. But we talk about these in terms of the number line, so x values moving from left to right. So this one is increasing from negative infinity all the way out to negative infinity. And I want to comment here, we always use the parentheses notation for these intervals. So recall from previous math classes, we use brackets on intervals if the end point is included. But right here, at this point of x equals -1, it is neither increasing nor decreasing. It's kind of the turning point. Okay, so for these intervals, we always use the parentheses. Okay, so parentheses, never brackets for these intervals of increasing. Okay, so between, notice here, -1 and +1, it is decreasing. Okay, so just moving from left to right, what's happening to the y values? They're getting smaller and smaller and smaller. And then from +1 all the way out to infinity, this thing just keeps getting bigger and bigger and bigger. The y values get bigger and bigger and bigger as we move farther to the right of the graph. So we would say again that this function is increasing from 1 to positive infinity. Now typically we would combine those two, so we would write this first interval of increasing, negative infinity to comma -1 with parentheses. We would write that symbol u in the middle, like the union. So negative infinity to -1. And then we would write this union. So this u stands for union. It's like set notation. It means this and this. Okay, so we would write this negative infinity, comma -1, and then a union, and then +1 to infinity after that. Okay, so I'm going to erase that. But you may see that in the homework. Sometimes the homework asks for like the union notation. Other times it asks just separate your answers by a comma. Sometimes either one. Just read the instructions. Make sure you are providing what my lab math is asking for. Now, intervals of increasing, decreasing are interesting to us. They can help us find these, we call them local extrema. So on this graph, for example, we don't have a true maximum, we don't have a true minimum. And why is that? Well, look at the left tail of this graph. So if we were to draw this out, let it keep going, these y values are going to get smaller and smaller and smaller. and then over here, the y values, as we get larger values for x, the y values get bigger and bigger and bigger. So this doesn't have a true minimum because it keeps going down. It doesn't have a true maximum. It keeps going up. As opposed to, say, like our friendly parabola over here, if we had just like a nice y equals x, this is a parabola with a vertex of 0, 0. That would be like the true minimum or the absolute minimum of that graph. Now here we don't have an absolute min, we don't have an absolute max because it keeps getting bigger or smaller in either direction. But we do have kind of these points of interest here. So when it changes from increasing to decreasing, right here at -1, that's not an absolute maximum, right? It's not the true highest point of the graph, but it is a point of interest. Okay, so relative to what's around it, relative to the y values that surround it, this is the highest peak that we see in that vicinity. Okay, so we call these relative maxima if it's like the largest local point. So they sometimes call them local max or local min, relative max, relative min. So here, this is relative to the points around it. This is a high point. Just like over here at +1, relative to the points surrounding it, this is a low point. So we call this a local min. We call this a local max. All right, so let's move on to some exercises. So here, the graph of the function f is given below. Locate values at which the function f has any relative maxima or minima. What are these relative maxima or minima? So read the y values from the graph as needed since the equation is not given. State the intervals on which the given function is increasing, decreasing, or constant. So of course there's a way to do this using a formula. So if you're given an equation for the function, here we're just given a picture. So we're going to start by just looking. And we move left to right, okay? So just thinking about like smaller values of x. So moving from the left and tracing this out, it looks like moving from -infinity out to around -2. So around -2. This thing has a decrease, right? So it's decreasing from -infinity till about -2. I know with the ticks on the graph, it can be kind of hard to see. I think that here, you know, maybe it's a little bit less than 2, but just for the sake of this problem, it looks like it's about 2. Okay. Now from -2 all the way up to 0, it's increasing, 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 right? So between -2 and 0, talking about the x values here. So moving from x equals -2 to x equals 0, notice the y values are getting larger and larger and larger. So we're going to say this thing is increasing from -2 until 0. Now what else? Starting here at x equals 0 and moving to the right, so we keep dropping down and down and down. Looks like right here between 1 and 2, so maybe like 1.5. It looks like it is decreasing from 0 until 1.5. So I'm going to combine these. I'm going to say it's increasing on this and also, so I'm going to draw a union here, also here from 0 until 1.5. And now finally, let's look at to the right of 1.5. So we start here and we move to the right. So all the way out till infinity. It looks like this thing keeps getting bigger and bigger and bigger. All right, so 1.5 all the way out to infinity. So those are the intervals of increasing and decreasing. Are there any intervals of constant? So recall like a constant function, for example, y is equal to 2, for example. That's just going to be a horizontal line. Okay, so it doesn't have a slope. That would be a horizontal line, just y is always equal to 2. That would be a constant function. Try to draw a straight line as best as I could here. But looking at this graph, really there are no pieces of just a constant. Okay, so it's either increasing or decreasing. In this case, there are none. Okay, so here under intervals of constant, I'm just going to write none. And then let's talk about what is the relative maxima x value. So here we're just going to do our best to estimate for like the minima. For the maxima, this one's pretty clear. So when x is equal to 0, y is equal to 4. So our point is 0, 4. But the relative maxima x value, it's located at x equals 4, and we obtain a value, x equals 0, and we obtain a y value of 4. Okay, so you can kind of think of these two together. We have a relative max or a local max. Those are used interchangeably at 0, 4. Okay, so when x is 0, y is 4. That is the relative highest point on this graph, located right here. All right, and so now we're going to have a relative minima x value and a relative minima y value. So just looking at the graph, looks like here and here, those are the two smallest points relative to what's around them in the graph. So we said that first one on the left was about x equals -2. Kind of a rough guess, right? So maybe if we zoomed in, we would see it might be closer to -1.5 or -1.75. But here, I'm just going to say it looks like it's around -2. And then on the right side here, the location of this one, we said is right in between 1 and 2. So I'm going to put this down as a 1.5. So when x is -2, when x is positive 1.5, we have a relative minimum. And what is the height of that minimum? Well, it looks like to me it's maybe just beyond -2. I'm just going to round and say -2 here. So we're talking about the height to where the y value dips down to. So we drop down here around x equals -2. It looks like around also y equals -2. And then again over here, when x is 1.5, it looks like y is also around -2, maybe -2.5 or so. But hopefully you see the concept here. I know with a small piece of a graph, it can be hard to see those exact values. But really, what are we doing here? We're looking just to see where relatively high points, relatively low points are. So right here, and right here. And kind of interestingly, those occur at the turning point. So when we changed from increasing to decreasing and vice versa. So our first one, we were decreasing until -2, and then it starts increasing at -2. So dropping down here and then here, that was our minimum. So at this value, x equals -2, x equals -2. Kind of cool to see that pattern. Right, next big thing we're going to talk about for graphs is tests for symmetry. Okay, so we want to determine whether the graph of each equation is symmetric with respect to the y-axis, the x-axis, or the origin. Okay, so we have tests to do this. So to test for y-axis symmetry, we're going to replace x with -x. So you just throw that number in, swap in a -x in place of x. Okay, if you get the same original equation, then it does have that form of symmetry. Okay, so here we plug in a -x into x squared minus 1. When you square the -x, you get back a positive x squared, which does match the original equation. So in this case, it does have that nice symmetry. So here, we're going to test to see if we have x-axis symmetry. So we're going to replace a y with a -y. So notice for this equation, -y has been replaced for a positive y, so we get -y equals x squared minus 1. If you multiply both sides by -1, you get y equals -x squared plus 1. Notice that is different from our original equation, so this one does not have x-axis symmetry. It did have y-axis symmetry. And here when I say like y-axis, x-axis symmetry, so here's our vertical axis y, here's our horizontal axis x, so this is x, this is y. So this x squared minus 1, what does that look like? It's a nice parabola. It's bumped down 1 unit. So here is the vertex, And so notice here the graph, and this is just a rough sketch. But here, if you were to fold this in half like a book, so imagine that the y-axis here is just like the spine of a textbook, maybe a pre-calc textbook. If you were to close that shut, it does have that nice symmetry. So this side to the left of the y-axis, this side to the right of the y-axis, you get the same thing. Now, if you consider like the x-axis symmetry, so now we're talking about this horizontally. So imagine you turn that book kind of sideways and open it up the other direction. So here, notice if we were to fold this in half, it doesn't have that same symmetry. So I'm talking about like this would look, for example, like that. Adobe's being a little bit slow. There we go. So before, it had that nice y-axis symmetry. Okay, so if you fold it in half just along the y-axis, it matches up perfectly. Now, if you were to kind of invert this, so flip it about the x-axis, it does not have that nice symmetry. Then finally, we can check to see if a graph or a function has origin symmetry. And so in order to do that, we replace x with negative x and y with negative y, and see if we get something equivalent to the original equation. And so in this y equals x squared minus 1, we replace y with a negative y, we replace x with a negative x. When you square that negative x component, you get back to x squared is positive. Multiply both sides by negative 1 to get back to just a y, so y equals negative x squared plus 1. That is not the original equation. So this does not have origin symmetry. It does have that nice y-axis symmetry. Okay, and then the origin symmetry, this one's a lot harder for me to draw. Imagine at the origin, you spin like, imagine it's a hinge, and you spin around the origin 180 degrees. Is that preserved? So I will try my best here. So here's our nice cubic function. Terrible at drawing, so please forgive me. But just imagine I grabbed, where each of these arrows are, I grabbed each corner with like one of my hands, and then I spun this around 180 degrees. Okay, so completely invert it. I would have the same exact shape and function. Okay. Maybe another easy one to think about would be like a straight line, just y equals x, for example, and spin that around 180 degrees, you would have the same exact line. All right, so let's move on to some exercises, and maybe here is where I will switch over to the document camera instead. And so we're going to apply each of those tests. So we're going to start to see if we have y-axis symmetry, and then see if we have x-axis symmetry, and then finally origin symmetry. So for the start, let me switch over here. I'm going to write down the problem. But the start is for y-axis symmetry. So y is equal to x squared plus 6. And now I will switch over to the document camera. All right, so y equals x squared plus 6. Let's start with y-axis symmetry test. Okay, so for y-axis symmetry, we're just going to replace the x with a negative x. So y equals, in parentheses, negative x squared plus 6. Okay, so what happens when you square a negative x? The result is just a positive x squared plus 6. And that does match up with our original equation, right? So y equals x squared plus 6. So does this have y-axis symmetry? The answer is yes, it does. Okay, so we're going to do the same with the x-axis symmetry. So we're testing for x-axis symmetry. We just replace the y with a negative y. We're going to solve for y, so multiply both sides by negative 1. That makes everything on the left now positive. Everything on the right will become negative, so negative x squared minus 6. And that is certainly not the same as our original equation there, right? So y equals x squared plus 6 is not the same as y equals negative x squared plus 6. Right, last we're going to check the origin symmetry, and that's just replacing y with a negative y. It's replacing x with a negative x, and then solve through. So here, negative y equals positive x squared plus 6. Multiply both sides by negative 1. We get y equals negative x squared minus 6. Okay, which is, once again, it's the same thing that we got from the x-axis symmetry test, but it is different from our original equation. So we'd say this graph does have that nice y-axis symmetry. I will try and do a little rough sketch. This is our parabola. It's bumped up 6 units. So it looks something like that. Okay, this is my attempt. The vertex is at 0, 6. You can see if you fold it in half, right, like a book, it does have that nice, beautiful y-axis symmetry. Now, if you were to fold that parabola across the x-axis here, it would not be preserved, right? So it would have kind of something like that. And then with the origin symmetry, imagine that you grab each of these arrows and then just rotate it 180 degrees. That would kind of make it frowning instead of smiling. So it would be a different graph. All right, our next problem was y to the 5th equals x to the 3rd. So I'm going to write that one down. So 2. Y to the 5th equals x to the 3rd. So y-axis symmetry test. We're going to replace y remains the same. Replace x with a negative x, so negative x cubed. What's nice about this, I'll kind of write this one out. Here we get a negative times a negative times a negative again. So remember, a negative and a negative makes a positive. So here we get positive x squared times negative x. Oh, excuse me, and this should have been a y to the 5th. And a y to the 5th. Okay, so negative x times negative x becomes a positive x squared. We multiply that by a negative x. So a negative times a positive makes it negative again. And so notice here, y to the 5th is still the same as y to the 5th, but negative x to the 3rd is not the same as positive x to the 3rd. So it fails the test for y-axis symmetry. Let's check for x-axis symmetry. So we're going to replace the positive y with a negative y. Really, there's a trick here. So as a reminder, we all know a negative times a negative makes a positive, right? And kind of using that fact, if you have an odd degree exponent of a negative number in the parentheses here, you're going to kind of have like an odd number out. So here I mean, negative y to the 4th, that would produce a positive. And then when you multiply that 5th negative y in, it's still going to remain negative. So this becomes negative y to the 5th on the left, still just a positive x to the 3rd on the right. So does this one have x-axis symmetry? Looks like no, it does not. Why is that? So does this match with our original equation? And the answer is no. All right, so let's check origin symmetry. So now we do kind of the 2 steps combined into one. So we substitute a negative x for x and a negative y for y. So here we get negative y to the 5th equals negative x to the 3rd. So negative y to the 5th, that would become negative y to the 5th. Outside of the parentheses, negative x in the parentheses raised to the 3rd, that will become negative x to the 3rd. What's kind of nice here is we have a negative on the left, a negative on the right. So if you were to multiply both sides by negative 1 or divide by negative 1, same result. We get y to the 5th is equal to x to the 3rd. And that's really nice. So that passes our origin symmetry test, okay? So it failed the y-axis symmetry, it failed the x-axis symmetry. but it does have that nice origin symmetry. Let's do one more example. And for these, you guys, while you're watching this video at home, I would invite you to pause the video and maybe try and work ahead. See if you get the same answer that I get. And then, if not, you can trace the problem from start to finish with me here. So we're going to do one more. X squared plus y squared is equal to 100. Great, so let's check for y-axis symmetry. So here we're going to replace the x with a negative x. So negative x squared plus positive y squared equals 100. Now, of course, here a negative x squared, that will just give us a positive x squared. Then the rest of the equation is all the same. So actually here it does have this nice y-axis symmetry. Let's check for x-axis symmetry. So x-axis symmetry, you replace y with negative y. So x squared plus negative y squared equals 100. Again, negative times a negative here will make it a positive y squared equals 100. So actually this one passes for x-axis symmetry. And then finally, let's see if it passes all three. Does this have origin symmetry? So negative x squared plus negative y, quantity squared, equals 100. And again, negative times negative, this will become a positive x squared. Negative y times negative y becomes positive y squared. And that equals 100. And so actually this does have all three. It has y-axis, x-axis, and origin symmetry. What does this shape look like if we were to graph this? Is actually the equation for a circle with a radius of 10. Okay, so we're gonna have some nice circle here. I'm gonna do my best attempt to draw. So just imagine this is a nice, beautiful circle with a radius of 10. So that's x equals 10. This would be x equals negative 10, positive 10, positive 10. All right, and so notice here, one property of the circle is if you fold it in half, kind of really anywhere, right? Take any like point from one end to the other, like across the diameter, that will give you any symmetry, right? So here, across the x-axis symmetry, fold it in half. We have that nice x-axis symmetry. Fold it in half like a book across the y-axis. We have that symmetry. And then the origin symmetry, so this one's where we rotate it 180 degrees, and we're just still back at a circle. Okay, so this has a nice one. It's got all three of those. All right, so to continue with the notes, why do we care about this sort of symmetry? Well, we have even and odd functions. So even functions have that nice trait of y-axis symmetry. So just think like x squared, for example, like that nice perfect parabola. You could just fold it in half like a book. Odd functions, they have origin symmetry. Okay, so to test if a function is even or odd, you can apply these symmetry tests. So we'll jump into some examples here. So determine whether each of the following functions are odd or even. So we have x cubed plus x as our first example. So determine whether this is even, odd, or neither. Right, so I'm going to jump back over to the document camera. And so how do we do this? I want to go ahead and check for if it's even, then it would have y-axis symmetry. So we're called to do that. We're going to replace the x's with a negative x. Oh, and this is equal to f of x. Okay. So f of x is equal to negative x cubed plus a negative x. In this case, do we have the same? So we get a negative x cubed and then minus an x. So this is not the same. This is not the same. Now we can continue. And I guess here, so f of x equals negative x cubed minus x. So really what we're doing is we're seeing is f of negative x. Is this the same as the original f of x? So here, I apologize for that, f of negative x equals. And so we're trying to see is if f of negative x is the same as f of positive x. So now we check for odd function. So does it have origin? And this is like saying, is negative f of negative x the same as f of x? Okay, sounds tricky, but really what we're doing is just, changing the y to a negative y, changing x to a negative x. All right, so negative f of negative x equals, this is negative, and then swapping in the negative x, we already checked that over here, right? So we checked the negative x first and got this negative x cubed minus x. So I'm going to go ahead and just take that and put it over here. So that's why I like to check the even first. So what I'm doing, put this in a bracket here. Checking negative f of negative x. Well, notice over here, we already have this f of negative x. So let's just put that over here. So negative, and then the brackets, negative x cubed minus x. So distribute the negative in, that makes this and this both positive. So we get x cubed plus x. And notice that is our original equation. So here, that is the same as f of x. So this does have the odd function property. So it is an odd function. It has that nice origin symmetry because negative f of negative x is equal to f of x. All right, I'm going to stop here for now and let you continue to work on these next few. All right, so picking up where we left off, top of page 14 of the printed out lecture notes, we were discussing the parity of a function, so whether it's odd or even. We talked last time about how even functions are symmetric about the y-axis, odd functions are symmetric about the origin. So just a quick recap for this first example. To determine if this x cubed plus x is even, odd, or neither, first we check if it's even. So if it's even, it has that y-axis symmetry. And to do that, we just check to see if f of negative x is equal to f of x. So here, f of negative x gives us negative x cubed plus negative x. This gives us negative x cubed minus x. That is not the same as f of x. Okay, so we can't use that. Fails this check. But let's check to see if it is odd. So odd functions have origin symmetry. So before we learned with x's and y's, so you replace the y with a negative y, x with a negative x. Here when you talk about functions like f of x instead of y, this is like asking the question, is negative f of negative x equal to f of x? Okay, and so I like doing it this way because we already have f of negative x here. So let's check. Negative, I'm just pulling this. This is already f of negative x. So negative, draw brackets around this, is negative x cubed minus x equal the same as f of x. Well, let's see. We distribute the negative in, so negative x cubed becomes positive x cubed. Negative x becomes a positive x. And that is the same as our original function, f of x. Okay? So that one works out pretty nice. It does have origin symmetry, therefore it is an odd function. Okay? So this one is odd. it's not even. Let's go through number 2. So g of negative x is negative x in parentheses squared plus a negative x. So this gives us positive x squared minus an x. Notice that is not the same as our original function. So no, this is not an even function. I'm just going to draw a line through here, and in this left column will be all of the even tests. In the right column, it will be the odd test. So left side, we're doing y-axis symmetry. Right side, we're doing origin symmetry test. So over here, I'm going to see what is negative g of negative x. So that is negative, and then in the brackets, I'm just going to copy what I have here, x squared minus x. Excuse me, that should be a positive x. Well, it's in the parentheses. So negative, and then bracket, positive x squared minus x. The negative is distributed to each term, so we get negative x squared plus x. Is that the same as our original function? And the answer is no. So actually this one is neither even nor odd. So here we have, this is neither. And then for our final example in this section, so h of x is equal to x squared minus 4. So h of negative x is equal to negative x squared minus negative x to the 4th. So here, negative x squared will become positive x squared. Negative x to the 4th will become positive x to the 4th. But still subtracting in the middle, since we are subtracting here. So, x squared minus x to the 4th, that is even. All right, and then let's see here. It's not going to be an odd function if it's an even function, but just to show you, let's do the test for practice. So negative h of negative x is equal to, we have negative, and then x squared minus x to the 4th. Here we get negative x to the 2nd plus x to the 4th. That is not the same as our original equation, so this one is not odd. It is, in fact, even. So this one was even, second was neither, the first one was odd. Alright, so that is how we test to see if a function is even or odd. Next, we're going to jump into the group of piecewise functions. So you may have seen these before in previous math classes. Piecewise functions just means it gives you two sets of instructions, depending on which part of the graph you're looking at. So it could be two pieces like this one, it could be multiple pieces, sometimes you get 3 or more. But in this case, it's just saying that f of x is 2x if x is less than or equal to 0. So any negative number or 0, we plug it into that top set of instructions. The bottom here says that f of x is equal to 2 if x is bigger than 0. So in other words, the right side of the graph, everything to the right of 0 is just the constant 2. Okay? So how do we handle these? How do we approach these? The first step is to just look at our input. Okay, so first we're prompted to find what is f of 5. Okay, so I'm going to think about that 5, that value for x. Okay, so when x is 5, are we going to use the top or the bottom set of instructions? Okay, the top is telling us if x is less than or equal to 0, well, 5 is greater than 0. Okay, so 5 being a positive number, that tells me we're going to use this second set of instructions. So here, f of 5 is just equal to 2. So it's always just that nice constant of 2. Next, f of negative 1. Okay, so here when x is negative 1, what is our y value? So think about which one of those sets of instructions do we use for the negative 1. The top one says if x is less than or equal to 0. So negative 1 being less than 0, we're going to use that top set. So here, f of negative 1, we're going to use that 2 times x. We're going to use negative 1 in place of x. So we get a 2 times negative 1 this gives us a negative 2. And then finally, for the next one, it says, what is f of 0? Okay, and for our instructions, that's kind of the cutoff, right? So x is less than or equal to 0, x is greater than 0. Which one do we use? We want to look for the one that has the line under it. So x is less than or equal to 0 up top here. We're going to use that because the 0, when x is 0, that is included here since we have the line under for the less than or equal to piece. So we're going to take 0 and plug it in. So we get 2 times 0, which is just equal to 0. Right, and then the last little section out of this lecture is going to be the difference quotient, okay? So I will jump back over to the Adobe. So the difference quotient is called that because up top we have f of x plus h minus f of x. That is just a difference, okay? So think in math, when you're subtracting, we call that a difference. If you are dividing a fraction, we call that a quotient, okay? So up top, the formula for the difference quotient, it contains exactly that. Up top is just a difference. On the bottom is going to be just this h every time. Don't concern yourself so much about what that h means. That comes a little bit later on. But for a function, we're given f of x. The first step is to find f of x plus h. So we did a little bit of this already, but we'll jump right into it here and show you guys what are the steps. Okay, so I'm going to write this down. F of x is equal to negative 2x squared plus x plus 5. Let me switch over to the document camera. All right. So we want to find the difference quotient. And that is f of x plus h minus f of x all over h. This is actually a really big concept for calculus, so those of you going on to that class, this is a really big takeaway. But the first step here is we already have this f of x, right? F of x is just given to us. What is this f of x plus h? So this comes from like your composition of functions, which means anywhere inside of our set of instructions or inside of our function, anywhere that you see an x, we're going to replace that with an x plus h quantity squared. So here, instead of negative 2x squared, I'm going to write negative 2x plus h squared. And then plus, instead of just adding an x, I'm going to add an x plus h in parentheses. And then finally, we can't forget about that 5. Let's do a little simplifying here. So recall, if you FOIL this x plus h squared, we've done a couple of these. Maybe I'll do it off to the margin. So x plus h times x plus h. If you FOIL this out, you get x times x is x squared. X times h is plus xh. In the middle, we have an h times x, but really the order doesn't matter. X times h times x. You get the same thing. And then finally, h times h gives you h squared. So I'm going to combine these two middle pieces. We get x squared plus 2xh plus h. The 2xh because we have both of those pieces in the middle. Right, so I'm going to take that and multiply by negative 2, basically. So this negative 2x plus h squared. Off to the margin, I FOILed out the x plus h to see what I get. So here we get negative 2 x squared plus 2xh plus h squared, and then plus x, and then plus h, and then plus 5. Let me go ahead and continue to simplify this. So I'll distribute that negative 2 in as promised. So I get negative 2x squared minus 4xh, that comes from the negative 2 times the 2xh, and then minus 2h squared. We add an x, we add an h, we add a 5. So just copying those from above. Okay, so this whole entire thing, this is our f of x plus h. That's going to go into our formula as the very first term. From that, we subtract this f of x. We divide the whole thing by h. We're going to get some nice cancellations. So here, f of x plus h minus f of x all over h. First, I'll put in the f of x plus h, so negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5. That is everything from the underline, so that is just our f of x plus h. Now we need to subtract f of x. That was our original problem. So our original equation here, so f of x is negative 2x squared plus x plus 5. That is what we are subtracting. So subtract negative 2x squared plus x plus 5, and then all over h. And this is where I wish I was on the right whiteboard so that I could very easily distribute that negative into the f of x that we're subtracting. But that's okay. These take a lot of space on your paper. So here, I'm going to leave the f of x plus h as the same. So negative 2x squared minus 4xh minus 2h squared plus x plus h plus 5. And now I'm going to distribute this negative into the parentheses here. So negative 2x squared, that will become a positive 2x squared, negative x, and negative 5 by distributing to these two. Whole entire thing divided by h. Alright, next let's try and cancel what we can here. So if we set this up correctly, then the only things left that don't cancel will have terms of h involved. Excuse me. So negative 2x squared, notice we have a positive 2x squared, so this and this will cancel off. We also have a negative x here and a positive x here, so that will cancel with that. We have a negative 5 and a positive 5, so those will go away. And so what survives? So up top we have a negative 4xh minus 2h squared plus an h all over h. So this looks very promising. Notice everything left up top still has an h involved. Okay, so negative 4xh minus 2h squared plus h. We're going to use the greatest common factor method to factor the top. So really what goes into each of these is just an h. So I take an h out of every representative from the top. So what's left from the first term is a negative 4x. What's left in the middle is a negative 2h. And then finally a plus 1 for the term on the end. All divided by h. And here we have an h on the top and h on the bottom. So this will cancel with this. And so for our final answer, negative 4x minus 2 times h, and then plus 1. So that is our difference quotient. Now, since we divided by h, we do have to caveat and say that h is just not equal to 0. And that is our final answer. So a lot of work for this difference quotient. Okay, that was the example given to you at the top of the page. I've got one more for all of us to do together, so maybe here's a good time to pause the video and go ahead and try and work on that next one on your own in the lecture notes. And then once you get an answer, maybe press play, see if we arrive to the same answer. Great, so for the exercise, we are given f of x is equal to x squared minus 4x plus 3. And we're trying to find the difference quotient. So that is f of x plus h minus f of x all over h. So first step that I like to do is just, before you try and throw everything in, let's just go ahead and find what is f of x plus h. So we found on the previous problem that we just swap in everywhere that you see an x, swap in an x plus h. So we're going to do that here. And the previous problem, and a whole bunch of these, you see that x plus h piece being squared, so x plus h squared is our very first term. It is helpful when you're learning, I would say, to just FOIL them out every time, make sure that you get the right thing. But once you've done so many of these, you kind of remember or can see that here you just get an x squared plus a 2xh plus an h squared as that first piece. Distribute the negative 4 into the x and to the h, so we get a negative 4x, a negative 4h, and then finally a plus 3. That is from our f of x plus h. So for the difference quotient, we're going to take that, make it our first term, we're going to subtract the original function, and then divide the whole entire thing by h. So let's do that. We have x squared plus 2xh plus h squared minus 4x minus 4h plus 3. That is just our f of x plus h. I'm going to subtract, and I'm always very mindful with my parentheses here. We're subtracting the whole entire original equation. So we're subtracting the original function, x squared minus 4x plus 3. So you want to make sure to drop down your brackets here, parentheses, because that negative does get distributed to each of these terms. And then the whole entire thing divided by h. Okay, so formula looks kind of short up here, a bunch of letters involved, but once we do our substitution, get a lot of terms down here. So step 2 is let's go ahead and distribute the negative into what's in the brackets here. So I'm going to copy down our f of x plus h. That stays exactly the same. So x squared plus 2xh plus h squared minus 4x minus 4h plus 3. Distribute the negative to the x squared, so we get a negative x squared. Negative 4x becomes a positive 4x, and then negative 3 at the end. All over h. And this stuff's kind of fun now that we've written everything out, because we get to cross a bunch of things off. So I notice here we have a negative x squared, we have a positive x squared, so let's get rid of that and that. Here we have a positive 4x and a negative 4x, so let's do away with that and that. And the last thing that we can do is get rid of this positive 3 and this negative 3. Alright, so crossed off everything that I could. And what remains? So let's write down the things I didn't cross out. We have a 2xh plus an h squared. We have a negative 4h. And really that's all from the top. We divide that by h. And a good way to check yourself on these is once you get to this step, everything involved should have an h remaining, because ultimately we do cancel that h. Okay, so the greatest common factor here, this term, and this term, they all have an h involved. So I'm going to factor out my h. I get a 2x plus an h minus a 4 inside the parentheses, all divided by h. This will cancel with this, and I'm left with just 2x plus h minus 4 as our final answer. Alright, that's all I have for this lecture, guys. I look forward to seeing you when we return back to campus. Enjoy the snow day, have fun out there, and stay warm.